Hello, Cal State Straub. We're heading off into chapter 11 now, starting today with these notes. So before we get into these notes, I need to make sure you have everything at your hands that you need. There was a worksheet that came along in the pacing guide with this. And as we do our notes today, you're going to go back and forth between that worksheet and the notes. So if you've not had a chance to print that out yet to have in front of you, you're going to want to go do that. The other thing you need in front of you is a calculator. Make sure you have that with you. And then also in the pacing guide, there was a little applet that I asked you to upload and be ready to use. So be prepared with your notes, your applet, and your calculator. Take a second to pause me and go get those things if you need. Okay. All right, now that we're ready to go, have the warm up in front of you here. We're going to do a quick one. From your notes that you took in outlining 11.1, you saw the parts of a hypothesis test, also called a significance test. I'd like for you to jot down those parts in Edpuzzle for me, and we'll take a look at them in a minute. All right, the next part of your warm-up is to review a CI from chapter 10. You're given some data here. If you'd please create the 95% CI, and in Edpuzzle, write me your conclusion that you came up with from that. Don't worry so much about the state plan, do conclude here. Just get me the CI for this moment. But you do know that you would normally do state plan, do conclude. Sketch. Okay. All right. Now that you've got both of those done, let's go take a look at the answers. Okay. The parts of the hypothesis testing. We will certainly be going through these in much detail with these notes, but I wanted to make it clear that you are still having state, plan, do, conclude. That is going to be with us the rest of this term, so please make sure you do that whenever it's asked for a CI or for a significance test. Within the state this time, you read about the null hypothesis, the alternative hypothesis. I call those the ho and the ha. Don't laugh, but that's just the way it comes up. The HO, the HA. Those are the symbols given to null hypothesis and alternative hypothesis. Just as we did in CI, we defined our parameter and population in our state. They were included. You need to make sure you list here what your population is and what the parameter is that you're doing the testing on. Usually I list population, list it, and then parameter, list it, so that it's very clear. Okay. All right. The plan is exactly the same 3 conditions as we used in CIs. The do has a new part to it, and this is the newness of this chapter. And there is a formula where you take the estimate. In our case, if we're going to start with means, that's the X bar, your point estimate. And you're going to subtract from that the hypothesized value, what it is that we're hypothesizing mu to be, and then divide that by our standard deviation of the statistic. So that's that sigma over square root of n if sigma is known, or it'll become S over square root of n when we do t distributions. So right now we're just starting with the Z statistic where sigma is known, and we will transition to the t statistic just like we did in CIs. Okay. Your conclusion this time, now you must label in it what your significance level is, what alpha has been, whether it's 0.05, 0.01, 0.1. Those are the common ones. That'll go along with your CI levels of confidence of 90, 95, 99. So we're going to use those. You must also put in there how your p-value that you get, the probability of this happening, compares to that alpha, and then you draw a conclusion of whether or not you want to accept HO or reject HO. And so we're going to learn all about that in today's notes, but those should be the parts that you have down. And if you didn't catch any of those, make sure to jot them down. There's going to be a Flipgrid video Wednesday where you're going to creatively tell me these parts. So you're going to want to have access to this. Okay, just real quick, check your CI that you should have gotten for number 2. This was a T-star situation because I don't know the standard deviation of the population. And so we went to the 1-bar stats and got our S and our X bar. And hopefully you got between 8.6 and 17.66 pounds. However, this is terrible because none of the three conditions are met. It's really not a great problem at all. You don't have SRS. There's an outlier, so it's kind of not great to use there, and independence is not met. Okay, so yeah, hopefully you got that. Now, what we're going to do is hop into the notes. If I can get back up to the first page. Okay, chapter 1, section 1 of chapter 11. And on your worksheet that you have, oops, let me pull that up if I can. And I don't know why. There it is. This one right here is the one you should have in front of you, Introduction to Significance Testing. And this applet that we're going to use in a minute. But right here, we're going to answer these first couple of questions from our notes before we go to this applet. So first, what is a significance test, and what's the definition of ho and ha? So significant tests, right here is your definition that goes there. This is a formal procedure for using the data that you observe to decide between two competing claims, two hypotheses. And the claims are going to be stated about a population's parameter, either mu or p, when we do proportions. Okay? And the basic idea here is that what we're doing is that an outcome that would rarely happen if a claim were true is going to be good evidence that that claim is probably not true. For example, if the claim says that the mean is 10 and we get a random sample with a mean of 20, and we run this statistical analysis on it and get a probability that that would be like less than 1% chance that that could happen, then what we're doing is saying, hey, based on what I got, maybe that claim in the first place was not good. So we would reject the claim. We would reject that reject the ho, sorry, that was there, and say we have evidence that that's probably not true. Now, is it still true? Yes, there's that 1% chance that ours could be way out there and that it could happen, but that's not very likely. Okay, we'll talk more about that, but that's the basic idea behind today. Okay, so your hypothesis must be a statement about the population's parameter. Okay, and then our results we get are expressed in this probability that says how well that our data agrees with the hypothesis. Okay. And again, just like in chapter 9 and 10, this is based on the fact that we're getting this results based on this procedure having been done many times. Okay. So we're going to start with a claim, but before we do that, I want you to go to your applet. So let me get out of this and show you how, how that applet works. All these things open here. Okay, where's my applet? There it is. Okay, you should have this applet ready to go. Let me explain it, and then I'm going to have you pause this and really spend a little bit of time with this applet. We're getting a claim from a state university that each of their players makes 80% of their free throws. Every player makes 80%. That's their average, okay? Or their proportion of shots averaged out many times, right? Okay, so that's a null hypothesis. Okay, it asks you on your worksheet to go to this applet and try several shooters to see what you think about their claim. And then also it asks you to write down the ho and the ha for this. Your ho is going to be that p equals 0.8. And then we'll talk about the ha when we come back after you've done some shooters. It asks you to set this at 100 and to check this box here to show true probability. What you'll do is hit the shooter, and then it'll just go 100 times, and it'll show you, actually here you'll see that the claim is up there in the purple, and the green is this player's average actually, and over 100 shots here, and it's still going. It'll tell you their percentage as it goes along. You could see that we're nowhere near with this player, the 80%. Okay, when you're done looking at that player, then you hit this button up here that says New Shooter. And so your worksheet asks you to try a couple of shooters and then answer on this. What do you think of their claim that each player hits 80%? And what's this evidence doing to make you think maybe they're not right or they are right? Okay, so pause here and go play that applet just a little bit. All right. If you've come back to after doing the applet, here's how I've written the ho and the ha. You'll see the HO here is P equals 0.8. The ha is P is not equal to 0.8. If you remember reading, that's called a two-tailed. We'll talk about that. Or you could make it less than 0.8 based on the look at the shooters I got. More of them made less than 0.8 than made 0.8 or higher. It didn't look like it was true based on on my samples. Maybe you have a different setup. Too many shooters had an average proportion way lower than 0.8. So that's kind of what we're looking at here. We're looking at our samples and we're going to compare those to the hypotheses. This university made this big claim and we're going, I don't see the evidence here. Okay, well, we can't just as statisticians say, it doesn't look like it to me. You have to have data to support that. And that's what we're going to be doing. We're going to be pumping data into a formula and getting an actual probability number that we can compare. Okay, so let's go back to our notes now. Oh, I misdropped. I did that again. Okay, it starts with a claim. So let's talk about this. Your claims are your null hypothesis and your alternative hypothesis. This is on your worksheet at the top where it asks you for the definitions of these. The null hypothesis is your statement of no effect, no difference, no change. They said that was 80%. We put P equals 0.8. Okay. So that we're going to take the claim as it is. Okay. The alternative is that we're trying to find out evidence for that. Well, we think that after looking at your players, we think it was less than 0.8. I'm not sure that's looking accurate to me. And so our ha might be P is less than 0.8. It certainly should be at least P is not equal to 0.8 because it didn't look like it to us from our sampling. Okay. So those are your two hypotheses. Make sure you have those definitions up on the worksheet that I have given you. All right, let's keep going with what do we do to set this up. Remember that your hypotheses always have to refer to the population. So ho and ha must always be stated in terms of the population parameter. You have your same three conditions. We mentioned that before, SRS, normality, CLT can be used here if it's means, or the other things we did if it's less than 30. And then for proportions, it's the NP, n times 1 minus P greater than 10 formulas. Independence is still your 10N. It's less than the population. Okay. The test statistic here is that estimate, your point estimate that you get from your sample, X bar or P hat, minus your hypothesized value. So if they said hypothesized was 0.8, our P hat was, I don't know, whatever we had different, and the hypothesized value is 0.8, then you divide that by your standard deviation of the estimate, which again is that sigma divided by square root of n if sigma is known. Okay, so there is that little formula. We have already jotted that down in the warm-up. Okay. But here you're seeing it again. Notice the notation here. The hypothesized value is the mean of the null hypothesis. So we call it mean sub 0, mean of the null. So notice that right there. We would also do sigma of the null, but I didn't have enough room to be able to stick it in there without it getting too tiny. All right, let's talk a little bit about p-value. This is new to us. So that this p-value, that's the probability value. So you'll notice that on your worksheet, you have a spot there to write down what is a p-value anyway. So here is, I just kind of put it in a nutshell. This right here that you could probably, the second paragraph could be what you could stick down there, some ideas. But here's stuff about p-value. Okay, if your test statistic is large and it's in the direction suggested by the alternative hypothesis, then we're going to have data that's like unlikely if that whole were true. Okay, and so we got to make that unlikely precise by giving it this probability value, p-value. Okay, so this is the probability that the observed outcome would take a value as extreme or more, because it could be the tail, the probability, it's the probability of the tail, whether you're going to the right or to the left, okay, that it takes that value or more, that probability, okay, all right, that's the p-value we're getting. Then that actually observed in the direction specified by the HA. So if the HA says greater than or less than, we're going in that direction. So assuming the HO is true, there's the chance I could get this or bigger or this or less if I'm going to the left. Okay. This is my chance. And so if that's pretty tiny, then we have strong evidence that that HO was probably incorrect. So the smaller the p-value, the stronger our evidence is against the HO. Okay. And evidence against the HO is going to give us evidence for our alternative. So since the HO is not very likely, it is most likely the HA is true. Okay. And that's how we make our decisions about the problems. Okay. All right. Let's take a look at a question. Okay. Here's a random sample of 400 paramedic call response times, and they got this mean. Last year, the mean of the population was 6.7 minutes, and it had a standard deviation of 2 minutes. So this is one of those likely events where this station could have its true sigma known. So this is going to be a Z statistic. Does the sample show evidence that these response times are improving? So you start off by writing your HO and your HA. So the HO here is that the mean is 6.7 minutes. Remember, the HO is that null hypothesis means no difference, exactly as stated. Okay. If they want to know it's improved, because improvement here means to get less minutes that it takes to respond, then our HA is that our mean is actually less than 6.7 minutes. So we want to try and find evidence that will show that hopefully that the place is improving, and that would mean that we could reject HO and accept HA as likely. Okay? So we're going to run our Z statistic here. Our mean from the sample was 6.48, the mean of the population, and then you put in your sigma, and your N was 400. I get a Z of negative 0.220. So when you go to the Z table, right, negative 2.20, that's on the left. So that tells me this p-value here, right, is this left-tailed, that's why it's called a left-tailed test, my Z being negative, because my sample statistic here is less than the hypothesized. It makes it negative, right? So that's that p-value right there. If I go to the Z table, negative 2.2 goes to 0.0139 on the table. So I just call this a left-tailed test, okay? We always have to sketch our distribution. Just like we did with CIs, the mean has to go in the middle. This time our mean of the hypothesis was 6.7. Then we need to state where we have our test statistic was 6.48. And then we shade the tail, this time left because it's less than, and show the p-value. What else you have to do is find this standard deviation piece, this right here, 2 divided by 20 would be 1/10. So you should mark off your standard deviations of 0.1. So this should be 6.6, 6.5. And so you could see we're going beyond 2 standard deviations away. So my p-value is quite small. Okay, it's 1.39% chance. Okay, so here's how we write our, I think that's good, our conclusion on this, or think about this. We're going to go to the Z table and get that p-value. So what it's saying is if that HO was true, then the mean response time this year is that it's still 6.7 minutes. Then there's a 1.39% chance we could get 400 samples with this mean time of 6.48 minutes. So that is so tiny that gives us strong evidence against the HO, and in favor of the HA. So we can go back to the person we've run the test and say, based on our sampling of this year's 400 of this year's times, we have strong evidence that you are responding quicker. It is less than last year. Okay. This is just your Z-table sketch, but you don't need to make Z-table sketches. You're going to make sketches using the mean and the X-bar like up above. But you can see that's what this means. You just got this teeny tiny area there to be your 2.2 standard deviations away from the mean. Okay, so therefore it is tiny probability. Okay. All right, so this is called a one-tailed test because it just goes one direction, left or right. This one was left, it could go right. So what about a two-tailed test? Got this little doggy here with two tails, okay? Two-sided, if you're not told in the problem to anything about less than or greater than, then we have to calculate it for two-sided, not equal to, okay? The problem is what we end up getting is one of the tails, and then in your very end, you have to multiply that by 2 so that you get the probability of being in both tails because you don't know if it's greater than or less than. So let's take a look at what I'm talking about. You have your Z table here, okay? And if it's two-tailed, if we weren't doing less than, if we didn't know, if we were just doing not equals to, then it could fall out here or out here where it is beyond that data point, and then we'd have to take that p-value in the end and times it by 2. Okay. So I just said example. If your HO had been that the mean is 6.7, and then your HA is that the mean is not equal to 6.7, then you would take this p-value and you would get a 0.0278, so 2.78% chance of it. And that's still significant there, usually 5%. And we're going to talk about that. That's your like 95% confidence interval was your cutoff. 5% is your cutoff for the most common 0.05 for the alpha. Okay. So if it's two-tailed, we just have that last step of remembering to multiply what we get in our calculations by 2. All right. This is the very bottom of your page, but before we do this, I'm going to ask you to stop and turn over the worksheet. And on the back of the worksheet, there are 2 questions, and I'd like for you to answer those 2. It just asks you to identify the parameter and the HO and the HA, the HO and the HA. Okay, and then we'll come back and look at how you did. Well, that one big. Sorry about all that. You're coming back to take a look at your back of your worksheet. Take a look here. I've listed for you the parameter that you should have listed. Make sure you put proportion or mean in it, and then put your context. And so here your HO was that the P proportion is 85%, so you put P equals 0.85. I always put it in decimals. And then it did not tell us that it was less than. It just says, let's see, how much sleep they got on a typical night. So it's not asking us if they wonder if it's less than that or more than that. So we just make it not equal to. If it's not stated, it's got to go to two-tailed. Okay. In number 2, your parameter now was mean, and put that in context there with your parameter there. And then the HO and the HA. This time it did say, it says we suspect the actual time it takes may be longer. So they gave us a hint in that problem there that we need to go greater than 10 because it's expected to be longer. Okay. All right. I know this is going long. Sorry, guys. We're almost getting there. We've got number 7, statistical significance to go through. The decisive value of P is called the significance level and it is written as alpha equals, alpha being that little fish looking thing. If the p-value is as small as or smaller than alpha, then we can say the result is statistically significant, and that's going to be in your conclusion. Since p equals 0.0139 is less than alpha, which equals 0.05, we have statistically significant evidence, and then we're going to talk about the rest, but that's to reject HO. Okay. Or we say since P equals 0.23 is greater than alpha at 0.05 or whatever it gives you in the problem, we do not have statistically significant data evidence to reject the HO. So we're going to accept it as likely. Okay. So I put in here the most common one is 0.05, but you would also have 0.01, 0.10. There's different reasons. Okay. So the final step in significance testing is then to draw your conclusion. So your conclusion is you either reject HO or you have to say this, we fail to reject HO. Okay, notice I guess earlier I said accept HO, but I know I was talking about HA, right? Accepting HA is okay. But notice we're not saying we accept HO. We're not proving HO is true because there's still a chance that with our sample, it still could happen 5% of the time. So we're not saying that HO is false. We're not saying HO is wrong. We're just saying we either reject it as being liable or we're going to fail to reject it. We don't have enough evidence. Even if our p-value is 0.05 and we get 0.06, that's still not very likely, right? But it's going to be greater than our p-value. So we have to say we fail to reject. Since p equals 0.06 is greater than alpha, which equals 0.05, I fail to reject HO. Okay? It's enough evidence that it's just not statistically significant for me to reject it. Okay? We just don't have enough evidence to do it. So if we reject HO, our sample result is just too unlikely to have occurred by chance. And so that's why we say it is statistically significant. But if it could have happened by chance, then we fail to reject HO and it's not significant at the given alpha level. So you might want to look at this slide, and on your worksheet it says statistical significance and decision making, and this slide right here would be great for you to put down on the bottom of your paper. I do want to caution us, big caution, your significance level alpha has to be stated before you get any data or do the t-test. Okay. Some people want to run a z-test or a t-test and they go, oh, I got a p-value of 0.06. If I make alpha 0.1, then I can reject it. And that's not being a reliable statistician. At the beginning, data analysis people need to say, okay, based on my context, here's where I need to set my acceptance level based on if it's medical, maybe I need it at 0.01, maybe I need it at 0.05, whatever your level is. And then you go run the data. And if it doesn't give you what you want, you can't change alpha and make it to be, oh, hey, if we change alpha, we can reject it. That's not being very reliable, okay? Not appropriate. So here we go. A couple of examples. A New England Patriots fan claimed that Tom Brady throws for at least 300 yards on average each game. We think it's less than that, okay? So the HO is that mean, the mu is 300. We think it's less, so our HA is mu is less than 300. We're going to take an SRS of 9 games, and I'm just giving you this. This is just data I made up. The mean was 295 and sigma is 15. Find the p-value, and let's see what we think of the claim. We look at this, and of course, we're going to do our conditions, and n is not greater than 30 here, so we can't claim CLT, and I didn't give you the data points, so we must proceed with caution. But in our do, we've got a z value, and we see that that gives us a p-value of 15.87%. So I'm going to stop the video right here and ask you to go to Edpuzzle and tell me, what would that tell you to do when you're making your decision about ho or ha? Okay. All right, hopefully you notice that p-value, that's pretty high, 15.87%. So we would look at this fan's claim and say, that's not really unreasonable, right? So basically in our conclusion, we're going to say, since p equals 0.1587 is greater than alpha at 0.05, okay, we do not have statistically significant evidence and we fail to reject HO. You have to say all of that every time, okay? By the way, you also need to go figure out your sigma divided by square root of n so that you on your sketch can mark off every 5 standard deviations, okay? Because it says draw, you got to draw that sketch. The claim of this was the mean was 300. We got 295 in our sample, and we're going less than, so we shade to the left and we show our p-value. And each standard deviation was 5. So we're only 1 standard deviation away. That's not too bad. That's why we did not get enough evidence. Okay. All right, another one. One last one, guys. The temperature in San Diego is claimed to be 70 degrees. We take a random sample of 25 days and get this mean and this standard deviation. Okay. We believe the temperature is higher. So let's see. What would be your HO? Is that mu equals 70? That's the claim, right? We don't change the claim. That's our null hypothesis. We believe it to be higher than that. So we say our alternative hypothesis is mu is greater than 70. Now we're doing a right-tailed. So here's where your sketch will be. Your mean is in the middle, 73. Oops, I think that should say 70. Oh wait, 72. Sorry about that. 72 is our data point. That actually should be down here, but I think I didn't have room to put them next to each other. So 72 is our X bar, and we're shading to the right because it's a greater than right-tailed test. And our S over square root of n is going to give us 3. So you could see that that's less than 1 standard deviation away, isn't it? So probably that's why these sketches are so important. When I make my sketch, I think, oh, I probably am going to reject HO here. I mean, fail to reject HO here. I don't have enough evidence. It's not tiny enough. So remember, this is your formula. So you'd go do your Z statistic. And I'm sorry about this. I put an S here, so we'd be doing T. This should actually be mu right here. So that's my bad. Z is 72 minus 70. And then we get a Z statistic of 0.6777. And when you go to the table, that goes to 0.7486. Oh, dear goodness, right? Okay. We're doing the greater than 70 thing there. And because we're going right-tailed, we're going to have to do 1 minus that, right, to get the right tail. So that's one other thing that I just needed to show you real quick. When you go right-tail, you have to remember, just like we learned back in chapter 2, to find the 1 minus that probability from the Z table. And we get 0.2514. So we have a 25.14% chance of getting what we got. If that was true, well, that's pretty likely, right? So remember, the smaller the p-value, the stronger our evidence is against that HO, and this is not very small. This is quite large. So there is not much evidence to cause us to reject the HO. So we would be saying, since p equals 0.2514, which is greater than alpha equals 0.05, we do not have statistically significant data. Therefore, we are going to fail to reject the HO. Now, we would have said, if it was small, we would have said we do have statistically significant evidence to reject HO and accept HA as likely. All right. Whew, we're done almost there. So remember, p-value is less than 0.05 is our general rule for rejecting the HO. Okay, that was a long lesson, and the rest will build from here and not be quite so big. So hopefully you can work on some homework tonight and practice some of these problems, and we'll talk about it in conference hours, or tomorrow's notes we'll pick up and go into it a little bit more. Bye. Okay, there it goes.